Hello everyone, now I would like to share our recent paper Metadata-Based Raw Reconstruction via Implicit Neural Functions, which is accepted by CVPR 2023. First of all, I will give a brief introduction of our work. Raw images is converted to sRGB images through camera ISPs, the memory cost of which is much smaller. However, for many low-level computer tasks, it is desirable to directly use raw images as input. Hence, many previous works focus on reconstructing the raw image from the sRGB counterparts. Meanwhile, to improve the reconstruction accuracy, a series of works propose to extract additional metadata to help the reconstruction step. In this work, we propose an implicit neural function, which helps our method achieve significant improvement compared with previous works. Next, I will introduce the background of our research. Raw images contain minimally processed outputs from camera's sensor. Compared with display-referred sRGB images, the pixel values of scene-referred raw images have the advantages of linear-to-scene radiance and higher dynamic range. As a result, raw images are beneficial to many low-level computer vision tasks, such as low-light image enhancement, super resolution, and high dynamic range imaging. However, raw images have mainly two disadvantages. The first one is that raw images have large memory cost, which are 4-6 times larger than sRGB images. This is because raw images have higher dynamic range, which is typically 14 bits. The second one is that raw images are not suitable for printing and display, as most display and printing devices are designed for sRGB format images. Therefore, many recent works advocate to map sRGB images back to their raw counterparts to avoid the drawback and utilize the advantage of raw images, which is also called raw reconstruction, or reversing ISP. Since raw images are converted to sRGB images by the camera ISP, which behave like a mapping function, it is theoretically able to map the sRGB images back to the raw. If we go deep into the ISP, we will find that ISP contains lots of procedures for the conversion. Among these procedures, there are many nonlinear operations, which will inevitably cause the information loss. Such information loss, as well as the raw sRGB mapping, are usually camera-specific or even image-specific, which means they are various based on camera type or even the parameters setting at capture time. To solve such problem, a series of methods propose to embed extra metadata into sRGB images at capture time, which is called metadata-based raw reconstruction. Now, I will briefly introduce some recent work. The first one is published in CVPR 2016. They propose to extract and store the necessary parameters for recovering a raw image from the sRGB counterpart. However, their main algorithm deployed on the device has high computational cost and only considers the global tone mapping. The second one is published in WACV 2021. They propose to use the uniform samples on raw images as metadata, and employ RBF interpolation using sRGB values and coordinates as input for reconstruction. Nevertheless, the fixed type of RBF interpolation does not take full use of the information from sampled data. The last one is published in CVPR 2022. They take a UNet architecture for sampling and recovering network to improve the sample's quality and reconstruction accuracy. However, their method requires to run a deep neural network on the device, which would lead to high computational cost. Based on the previous methods, we build the proposed method. This is the overview of our method. At capture stage, we follow reference to implement a uniform sampling on the raw image to generate the metadata, which is then embedded into the sRGB image. At reconstruction stage, the metadata together with corresponding sRGB samples are used to train the implicit neural functions, which then convert the sRGB image to the raw image. The network structure of INF is a two-branch MLP with siren layers. The inputs of INF include sRGB values and its coordinates, and their branches are regularized with different parameters of weight decay. INF is trained in a self-supervised manner, which requires no pretraining on any type of cameras or data sets. Moreover, Inspired by reference, we also introduce a patch-specific training strategy to make INF robust to the local tone mapping. Specifically, we split each image into patches, and use the samples from each patch together with its 8 neighbor patches to train the patch-specific INF, since the mapping of each patch and its neighbors are supposed to have strong relationship. Here is the results and applications of our methods. For quantitative comparison, we evaluate on the CAM and NUS data sets, where CAM dataset is downsampled from NUS dataset. Such downsampling will undermine the strength of local mapping. Nevertheless, our method still significantly outperform the previous method, which can be attributed to expressive power of INF. Here is the qualitative results. As can be seen from the error maps, our method significantly reduces the reconstructed error on the whole images, especially the saturated regions. For more results and experiments, please refer to our paper. Next, I will show 2 applications of our method. The first one is guided depth super resolution. As can be seen, the INF with ReLU outperforms the previous self-supervised method PIX transform. Here we suppose that ReLU is more suitable for depth super resolution, as ReLU is piecewise and discontinuous, which fits the depth discontinuity of the sharp changes near the object edges. However, the results of INF still have better visual quality. The next one is low light image enhancement. As can be seen, recovering from the reconstructed raw images by our method achieves much high quality. Note that we do not mean to compare it with other methods, which is only used for reference. For more detail, please refer to our supplementary material. Here is the conclusion. In this paper, we make a first try to introduce the recent success in implicit neural representation into raw reconstruction problem. We design an implicit neural function trained in a self-supervised manner, which require no pre-training on any type of cameras or data sets. We conduct extensive experiments on different cameras and demonstrates our algorithm significantly outperforms existing works. We show that our framework is also suitable for other tasks such as guided depth super